Bismillahirrahmanirrahim. This is our lecture 8. So in this lecture, we actually learn a very small things. That one is the modern theory of metals, determination of Fermi energy level, and the average energy of an electron. Okay. So this one is the syllabus. Now we will learn this thing from the Kasab book. So this one is article number 4.7, quantum theory of solids. Okay. So we will start from article number 7.1, free electron model. Okay. So in this article, what we actually learned, we actually derive the quantum theory of metals. So we'll just derive the average energy of an electron and the Fermi energy level of an electron. This electron in a metal. Okay. Now, uh, look, in this chapter, what I actually need, uh, we need to just recap our previous things. That means we have to recap our fourth semester things. If you can remember, I will also show you, but I will not go in details of that things. Okay. So they have written. We know that the number of GE. So can you remember what is called the state function GE? G is the probability of getting an electron, and the unit of this GE is per unit energy per unit volume, and they prove that GE is proportional to e to the power half. So from where we have known this, we derive these things. So if you go to the your Neyman book, then you will see in chapter 3, that one is in chapter 3. Can you remember these things, the density state functions, the mathematical derivations? I have shown these things in our theoretical class. So today in our lecture, we will not show in details about this derivations. Just we will see from where these derivations have come. Okay. So this one is the mathematical derivations. They from the Schrodinger's one-dimensional equations. After they solve the Schrodinger's one-dimensional equations. Can you remember these things? Can you remember this figure? The two-dimensional array, the quantum scales in K space. I think this question was either in the midterm or in the final. So look, if you derive these things, then finally you find. Look, if you derive these things, then finally you find GE should be equals to 4 pi 2m to the power 3 by 2 divided by h cube root e. So look, this total part is a constant except root e. So we can write down from here, or we can conclude from here that our GE, our this GE should be proportional to root over e, isn't it? So that's how what they have written, or they have concluded, that GE should be proportional to e to the power half. So you can also, if someone have any confusions, you can also go through your previous things. Then you can conclude that GE is proportional to root e. And we have also calculated the Fermi-Dirac probability function. If you can remember the Fermi-Dirac probability function, so can you remember that Fermi-Dirac probability function? That means the probability of finding electron. That curve is something like this. Okay. So I can also show you. Maybe here they have shown. So can you remember this figure? Fermi-Dirac probability functions. I think you can remember. Otherwise, you can also go to your Neyman book, and from the Neyman book, you can also find out the figure. Okay, so I'm not showing you the figure. Okay, now, so we have also and that Fermi-Dirac probability functions is denoted by Fe, if you can remember. Now, so if we go through the energy band diagram, then if you go to this figure, then this one is the Fermi-Dirac probability functions of GE. Sorry, this one is the probability of getting an electron is GE, and this one is the Fermi-Dirac probability function. Okay, and Then what we can find out? So at absolute zero temperature, the energy level up to EF. So can you remember EF? EF is the Fermi Dirac level, and at 0 Kelvin, this one should be equals to zero. So uh, if we look that the probability of Fe in terms of Fermi energy, then Fe at 0 Kelvin, Fe value equals to 1. So where E is less than F, and if E equals to 0 if E, the or the energy is greater than the Fermi energy level. So at 0 Kelvin, EF separates the empty and full energy levels. I think this up to this clear. Now at some finite temperature, Fe is not 0, so that one is beyond EF, and we have also shown that things in our figure. So if you look this figure, so this one is the concentration of an electron, if you can remember these things. Now the distribution of the electron or the concentration of the electrons, that one is denoted by Ne, should be equals to multiplication of Ge and Fe. Now since Fe equals to 1 for E is smaller than Fermi energy level, then the step functions Ne should be also proportional. So that means if your Fe value equals to 1, then Ne should be equals to Ge, and if Ge is proportional to e to the power half, then Ne should be also proportional to e to the power half. Is that okay? Okay. Now the energy, that means the Fermi energy level of an electron in a metal. So that one is the Fermi energy level, or the Fermi energy level or the distribution of an electron. That one should be N equals to, we have to integrate from 0 to top of the band, Ne dE. So what is the value of Ne? Ne should be equals to GeFe dE. Okay. So now if we put the value of Ge and Fe, if we put the value of Ge and Fe, then our equation should look like this. So you can find these things from equation number 4.10 and equation number 4.18. Okay. So now if we integrate these things, then we can conclude that EF0 means that one is at 0 Kelvin. So at 0 Kelvin means your this T value or this temperature value should be equals to 0. So exponential e to the power 0 means 1, right? So 1 plus 1, so 1 plus 1 equals to 2. So if we integrate these things, so please take your pen and paper. I have done this integration. This one is very simple integration. So what you actually have to do, that one is e to the power, uh, that one is root e. You have to just integrate the root e values. Then you can control, and whenever you put the value of t equals to 0, then this value should be equals to root e. Write down that one is EF 0, because that one is at 0 Kelvin. Then you will find that EFO should be equals to, that one you will find that EFO equals to h square divided by 8 Me 3n by pi 2 by 3. So this one is very easy integration. You try to solve these things by yourself. This question is important for the exam. So if you fail to complete this integration, then I can also show these things. Okay. Now that the Fermi energy level, so this one is for for T equals to 0 Kelvin. Now if the question is come that at T equals, that means for a certain temperature, then what you have to do, you have to just integrate these things, integrate that thing, and that one should be EFT. That one should be EFT. And try to complete again. I have solved these integrations also. If you face any problem, then I can also show this integration. But think you should solve this thing because you are in the fourth year and this one is not very difficult integration. So if you complete this integrations, if you complete this integration with respect to dE, that means root over e divided by 1 plus e to the power something t. So the integration is something looks like this because this total part is a constant part. This total part is a constant part. So if you complete this integration, if you complete this integration, then you will find that EFT should be equals to EF0. What is EF0? That means at 0 Kelvin. That means you will get this term as a constant term. That one is EF0 and this one as the rest of the integration part. Okay. So this one is the Fermi energy. This one is the Fermi energy of an electron in a metal at T Kelvin. Okay. So if you change the value of T, then you can easily find out the Fermi energy. So this question is also important. So if the question comes like this, determine the Fermi energy level of an electron in a metal at T Kelvin. Then you have to write this thing. And if the question comes, determine the Fermi energy level at T equals to 0, then you have to prove up to this. This one is also, again I'm repeating, this one is important. Please complete this integration. Again I'm repeating, please complete this integration. And the next part is the average energy level. If you look at the syllabus, what is the contain? That one is determination of Fermi energy and average energy of an electron. So we have completed up to the Fermi energy level. And the next part is the average energy level of an electron. So from here, this one will start the average energy level. So if you want to find out the average energy level, then how to calculate the average energy level? So E average should be equals to, you have to integrate E N E. N E means the distribution of the electron. You have to integrate with respect to D E. Then you have to integrate N E D E. So we have to substitute the value of G E and Fe value in place of N E value. Okay. Then if we integrate these things, then if we complete the integrations just as similar integrations like example 2.1 of your CASA book, so then E average 0 should be equal to 3 by 5 EFO. So what is EFO? You know what is the value of EFO, right? So if the question comes like this, determine the average energy level E average 0 in terms of EFO, then you have to complete this thing. If the question is not like that, then you can also keep that in place of EF0, you can also keep the value of EF0. No problem with that thing. Okay. Now at absolute zero temperature, so this one E average 0 means at 0 Kelvin. That means whenever you put the value of uh, GE and Fe value, you have to put the value of temperature T equals to 0. Okay. Now, if this one is not like 0, that means T is not like 0, then what will happen? Again, same things. You have to integrate that EF equals to, how do we have integrated EFT equals to this? Similarly, we have to integrate the same things. These two integrations are similar. So then you will find that E average T should be equals to 3 by 5 EF0, 1 plus 5 twice square divided by 12, 80 divided by EF0 whole square. So this one is the average energy of an electron. Okay. Now the next part is, so we know that half mv square, that means the kinetic energy equals to average energy, that means average energy of an electrons, and that one is 3 by 5 EFO. So we can say that this VE is called the effective speed or known as root mean square speed of an electron. So we can find out the relationship between the velocity and also the average energy. We can also find out the relationship with the uh, Fermi energy level uh, and so on. And again, we know that the kinetic energy E should be equals to 3 by 2 kT. So same way half mv square equals to 3 by 2 kT. So from the same formula, we can also conclude the relationship between the temperature and the velocity, because this m value and this k value both are constant. So this velocity v is proportional to root t, isn't it? So this one is the relationship between. So if I ask in the exams what is the relationship between the effective speed and the temperature, if that one is a short question, then what is the relationship? You just write down from here, from this line, you can conclude that the relationship between the velocity and the temperature is directly proportional, but root t. So again, similarly, if we want to find out the relationship with the temperature, then we know that this temperature is proportional to the temperature, and here this one is not t to the power 3 by 2, but we have seen in the chapter 2, this one is not t to the power 3 by 2. Okay, so very simple things. So from this topic you will get, one theoretical question. So what you have to do in your room, that means you have to derive this equation. I have also derived these two equations by myself. So this one is not a very difficult equation. If you use your that means the integration knowledge, that means how to solve the integration, then this one is very simple things. Okay, please try to complete these things by yourself. And you can also consider these things as your assignment also, no problem. Along with your mathematical problems, you can also consider these two derivations, or these four derivations as your assignment. Okay, and side by side, I'm not going through this conduction in metal. No need to go through article number 4.7, because this one is not included in your syllabus. So no need to go through these things. Okay, but what you actually go through by yourselves, that one is try to solve the example number 4.9. Calculate the Fermi energy EFO at 0 Kelvin for copper, and estimate the velocity of the conduction electron is this. The density is like this. Relative atomic mass is 63.5. Okay, so try to solve these things, and no need to solve the example number 4.10, and try to solve the similar type of problems related to example 4.9. So this one will be included in your midterm exam. Okay, so I'm skipping the conduction of an electron in a metal, because this one is not included in your syllabus. Okay, so up to this one will be your syllabus. So look, so most of the things from this book is similar type of mathematical problems. If you solve one numerical problems by yourself and try to understand the numerical problems, then the rest of the part is easy. And I have checked the your class test script, and most of you have made your mistake. You made your mistake in unit conversion, and almost I have found almost 75% students just copy and make the same mistakes. So I'm very disappointing about for this. So I think the syllabus is very small for the midterm, and try to go through these things. Okay. So here I this on here I would like to conclude our midterm syllabus, and then next after midterm we'll start from the dielectric properties of material. Okay, so from after midterm we will start the dielectric properties of material, and the magnetic properties of the material, then the introduction to the superconductivity. Okay, so hope for the best for the midterm exam, and I'll see you after midterm, inshallah.